do any of these other things, I want to look at some of these AP style questions, just so that we get a better idea as to how to do some of these based on what we did last time. So the first one we'll look at, this one is 2002 Form B. And there should be both, I don't know if I printed out the answer to this somewhere. I may not have.
I think you have it.
I don't remember if I did. It doesn't really matter. But I did print out the 2002. But it doesn't matter. So it looks at down here, they say to take, it says to take this graph, take this diagram, which this is a galvanic cell, electrolytic cell, a galvanic voltaic cell, where they show the electrons going from M to E. So the idea is they say identify M and M plus 2 and then specify the initial concentration of M plus 2 in solution. So they want to know well, M is where the electrons are coming from. So that M must be the place on here. Maybe I should even pull it up on this, pull it up on the front screen here. It would be better to do that. Here's number 1. I think this is it. I think it makes it easier if I put it up front so you can see it. Turn out the lights. So since the electrons are leaving here, this is where the oxidation takes place. Therefore, this M must be the anode. So what they want me to do here is when they say identify M, they want me to go back to the reaction and identify which one of these zinc or nickel solid is M. So when I look at this, zinc goes from 0 to a +2 charge. Well, in order to do that, to get more positive, it must have lost negatives. So it looks to me as if zinc is being oxidized and the nickel is being reduced. Which would mean if they say what is M, M is the zinc, Zn, and then M plus 2 is the zinc plus 2. That's what they wanted here. Specify the initial concentrations in the solution. Well, the initial concentrations of these solutions, I don't remember if they say it here. Well, they tell me they're two standard.
Have your attention. Key Club meeting is starting at this time in press box 2. Key Club meeting is starting at this time in press box 2. Thank you.
So if these are standard potentials, these are at standard conditions, which must mean this is in a 1 molar solution. So then again, M was zinc, M plus 2 is the zinc ion, and the initial concentration of M plus 2 must be 1 molar.
Mr. Scarcelli, please call 5741. Mr. Scarcelli, 5741.
Then indicate which of the metal electrodes is the cathode. Well, we said since the electrons are generated at this electrode, that is where oxidation occurs. Therefore, X must be the cathode. So which of the metal electrodes is the cathode? X. That is the one that is gaining electrons. Write the balanced equation for the reaction that occurs at the cathode. Well, it would be taking this initial reaction and writing the nickel half reaction. Nickel plus 2 electrons goes to nickel. Okay, that's part B. Really an actual pretty easy question to answer. What would be the effect on the cell voltage if the concentration of zinc plus 2 were reduced to 0.1? Okay. So again, this goes back to our discussion of Q last time. So essentially, it's like removing product. Well, if I remove product by taking this down to less than 1 molar, the reaction shifts towards product. So what is the effect on the cell potential? If it goes more towards the product, the E0 will increase. Higher voltage. And then lastly, part D. What would happen to the cell when the salt bridge was removed? Well, what happens when you remove the salt bridge?
It stops working.
Stops running. The cell shuts down. Why? Because there is a buildup in charge in each of the two cells, therefore the voltage becomes 0. Okay. So that was actually a pretty easy one to get from the last time. Another one that I gave you, let's see if I can find one more recent. I have 2004. The sixth one involves more calculation. Go back to this one. this 2004 question. This was another good one. This one had some pictures of another cell. So I can do that one. See if this is question 2, if I remember which one it is. Yep, that's it. So they give me, oh, that wasn't, that was the other one. Sorry, let me look at 3. Yeah. Okay, so they give me this cell and they say, write the balanced net ionic equation for the spontaneous reaction that occurs in the cell. So what they're assuming that I'm going to do is look up these reactions. So I'm going to have to do that. I'm going to have to go into the packet that they give me, and I'm going to have to look up the silver and zinc, because I think that's all they give me, nothing on the top right good. So I'm going to have to look up Ag, the reduction potential, so Ag plus 1 electron goes to silver, and zinc plus 2 electrons goes to zinc. I'm going to need to look up their E0 values, and I would find the following. If I look on here, silver plus one electron is 0.80 volts, and the zinc plus 2 is negative 0.76 volts. So when they say write the balanced equation for the spontaneous reaction that takes place in the cell, what I need to figure out is which is more likely to be oxidized, which is more likely to be reduced. How do I know that? Which one of these is more positive? Look, that would be the E0 reduction for the silver. Now what does that tell me? It tells me that it's more likely that silver will be reduced than zinc. So if silver is more likely to be reduced, the zinc is more likely to be oxidized. So that I would write this reaction then as silver. The silver plus 1 electron goes to silver, and the zinc goes to zinc plus 2 electrons. So it would seem that 2 silvers, so there's a plus there, 2 silver ions of zinc goes to 2 silvers plus zinc plus 2. That is now written in terms of my most likely oxidation, here, my most likely reduction. What's the standard potential? Well, the E0 of reduction is 0.80. The E0 of oxidation is 0.76. When I add those up, I get 1.56 volts. In the diagram above, label the anode and the cathode. Okay, well, it seems to me that silver is being reduced. The reduction occurs at the cathode. So they would have wanted me to write cathode here. Then it would mean that zinc must be the anode. That goes here. This is interesting, and I wanted to show you this because this is one, since this is the anode, the zinc, where the electrons are leaving from, where the electrons actually flow in a counterclockwise direction, not the clockwise that we keep seeing. Indicate in the boxes below the half cells the concentration of the silver and nitrogen. Okay, well, this tells me they need to be standard reduction, or standard conditions.
So 1 molar.
How will the cell potential be affected if Ki is added to the silver half cell? Ooh. If I add Ki to this half cell, right? What is the problem with what's already in here? This is silver metal, and the solution has silver ions. When you add Ki, you're adding potassium and, most importantly, iodide ions. The iodide reacts with the silver to make silver iodide. Now, why does that matter? The concentration of the silver goes down. So if I look at the reaction, the concentration of silver goes down, So it's like removing reactant. The reaction shifts towards the reactant. E0 becomes more negative. So it decreases in the cell potential. Okay? So those were two that I thought were really good in that they kind of looked at everything we did last time and kind of summarized it all. The only other one that does the same thing was this one from 2003, which was one I just had up too. And I'll get rid of this here. And I'll bring this up real quickly. They give you all the parts, and then they say to you, calculate the standard cell potential for the reaction in part A. So part A says you have several different cells. They want to know, write the net ionic equation for the cell that would have the greatest positive E0. You need to look up the E0 values for aluminum, copper, and iron, and pair up the one that has the most positive reduction with the most positive oxidation. Those two would then be the one that has the most likelihood of producing the greatest E0 value, the greatest positive E0 value. Once you do that, they then want you to calculate the E0. And then when they do that, they say the cell is constructed based on part A, label the metal used for the anode and the cathode. I mean, again, you're just looking at which one is oxidized and which one is reduced. Okay? So that you can see what we did last time. It's really not that much. It seems like a lot, but it really isn't. Okay? The last portion of this, and it isn't obviously everything, but the last portion that we look at is an electrolysis reaction. Electrolysis reactions are reactions that are non-spontaneous. It is continually supplying energy to something. And they can be done in one of two ways. One is in the molten state. This is molten sodium chloride. So it is sodium chloride, the salt, that has become a liquid. So that what you see is you have an anode here, which is some metal, and you have a cathode here, an inert metal, one that will not react. Good one would be platinum, so that it wouldn't do anything in the reaction itself. Now, this is just the molten chlorine, so that the molten chloride going to chlorine. So what you see is, in this case, here is the difference. The anode is still where oxidation occurs. The cathode is still where reduction occurs. So none of that has changed. But notice that there is a positive sign here. The reason the positive is near the anode is because the electrons are being pulled away from the anode. In this case, electrons are not willingly lost, they are pulled by the voltage source. It is forcing the oxidation to occur, forcing the electrons toward the cathode. So that in this case, what you're seeing is sodium chloride in the molten state would be sodium ions going to sodium metal. And chloride going to chlorine gas. Now, if you look up the E0 values of this, what you would see is that the sodium, way on the bottom here, somewhere it should be, is a negative 2.71 volts. The chloride going to chlorine, let's see if I can find that too, would be negative 1.36 volts. This tells me this is very non-spontaneous. So that in order for this
That would be
reaction,
negative 4.
What's that?
It would be negative 4.07, wouldn't it?
0, 1, 2, 3, I'm sorry, 4. Sorry, I missed that one. This reaction is highly non-spontaneous. So what does that mean? Well, it means that I must supply a voltage of greater than 4.07 volts to allow this reaction to occur. When it occurs, you see chloride has only one option of going to chlorine. Well, in order to do that, the chlorine, this would be oxidized. So you'll see at the anode, your chloride is becoming chlorine gas. You'll see that your sodium ion is being reduced to make sodium metal on this cathode. That is the essentials of an electrolysis reaction. And you see the same thing here. Now, a molten electrolysis reaction, very, very easy to figure out. Here is your anode again, your chlorine gas. The nice part of this is that let's say that you did a reaction like this where you were able to induce this reaction. You could take this chlorine gas that you produce, you could bubble it through a cold sodium hydroxide solution and make sodium hypochlorite or bleach. Okay, very common process to do that. And then you could make sodium metal on this side, which we could use for various purposes. This is an electrolysis in a molten solution. Now the complicated portion of this. What if it were not in electrolysis in molten solution, meaning this is just sodium chloride liquid, which just goes to sodium and chloride ions? No, no, no. What if it were aqueous? Now the complication. When it's aqueous, what is also in solution besides sodium and chloride?
Water.
Water. So what you must consider is, okay, I know that sodium can be oxidized. I know that sodium can be reduced and chloride can be oxidized, but isn't it also possible that water can be oxidized and reduced? So the trick to one of these reactions, a reaction that occurs in an aqueous solution, is you must also account for the oxidation and reduction of water. This is what you've seen in those reaction predictions, where it will say the electrolysis of, in this case, an aqueous sodium fluoride solution. So that what I'm going to do is I'm going to look at sodium fluoride. The sodium is gaining an electron to go to sodium salt. The water could also be reduced. So what I must consider is, here is my reduction of sodium, here is my reduction of water. The negative sign indicates that both of them are
non-spontaneous.
But what does this number compared to this number mean?
It's easier to reduce water.
It's easier to reduce. So that when this occurs at the cathode, you won't get sodium metal, you'll get hydrogen gas. So that when you do an aqueous solution, now the complication is you must consider water. Now water is also, I believe, on our reduction potential, somewhere on here. There's the one water. I see water. This is water being oxidized, so water reduced should be here. Here it is. So right down here, it does have water being reduced. So I could look at the reduction of water and I compare. So what it tells me is for sodium fluoride, this is the reaction I expect at the cathode. So then I would also look up now the anode. Well, the anode would be fluoride going to fluorine. So I looked up that number. The easier of reduction is given, so that means the oxidation is negative 2.87. Well, when I do the oxidation of water, I don't know, I must have just put that, but you would know it would be negative. So when I put in the water value, water going to oxygen and H plus and 4 electrons, notice what happens here. I get a number that is negative 1.23 volts. And again, this is my oxidation, so that's why you have to consider a negative here. Which is less negative? 2.87 negative or negative 1.23?
Negative 1.23.
It's the negative 1.23. So that for sodium fluoride, it is easier to reduce water and oxidize the water that is there so that you actually get water breaking down to hydrogen, oxygen, hydroxide, and hydrogen. Oh, guess what these make?
Water.
Water too. So that these waters, the 4 of them, cancel out 4 of them over here, so that really what you're seeing is water breaking down to hydrogen and oxygen. That's the small complication you get. Not as small, I guess. You must consider water whenever you're doing an electrolysis in an aqueous solution. It's a little easier when you have a molten solution because there's nothing else there but those ions. And to be honest, that's it. There's nothing more to it. So that if I go down here, this is just kind of the sodium chloride one. So I give you the electrolysis of AgF. Well, if it's the electrolysis of AgF aqueous. So let me look at AgF. It would probably be easier this way. Maybe, let me see if there's... Let me do this. It would be a lot easier to go down here. I'm just going to try two of these. The molten NiBr2 and then the solution. So when I do this, the NiBr2, if it's molten, I only have nickel plus 2 and Br minus. Well, nickel plus 2 can go to nickel. It does that when it gains 2 electrons. Bromide goes to bromine when it loses 2 electrons. I have nothing else there to consider. What is the minimum energy needed to do this? Well, for the nickel plus 2, so find it here, nickel plus 2 is negative 0.25 volts. The bromine is going to be negative 1.07 volts. So I get 1.32 volts that would be required. When I do it in an aqueous solution, I have to consider that this is also present. 2 waters plus 2 electrons go to H2 plus 2 OH minus. The E0 of this is negative 0.83 volts. O2 plus 4H plus 4 electrons goes to H2O, 2 of them. The E0 of this reduction is 1.23. I gotta write that the other way. I wrote that backwards, I'm sorry. This is water goes to O2 plus 4H plus 4 electrons, and that's negative 1.23 volts. So that in an aqueous solution, I would then consider the oxidation of water or the reduction of water or the reduction of nickel. Which is less negative? Negative 0.83 or negative 0.25?
Negative 0.25.
So that it's easier to reduce the nickel than it is the water. So that my reduction is Ni plus 2 electrons goes to nickel. Then, which is easier to reduce? To oxidize? Water or the bromide?
The bromide.
Bromide. In this case, the water isn't even considered. You would do that in every one of these examples. Now, the only thing that we haven't discussed is this last portion. When you're going through this, when you do an electrolysis, it is also possible that if you were going to take silver ion and make silver metal, that process of electrolysis, and we can think when we did the atom going all the way back to Faraday, you can actually calculate the amount of silver solid that should plate out. Now, in order to do this, you have to know a few things about electricity. I'm going to go down because all of this we don't really need to know yet. I don't think we need to do that. See if I can find, might actually be at the bottom. Okay, well, then let's look at what we can do. If I were to solve some of these questions, and questions like, let me just go to the question and then show you how I would solve it. It says a current of 1.5 amps is passed through a silver ion for 15 minutes. The voltage is such the voltage is such that silver solid is deposited on the cathode. What will the mass of silver be deposited? Now, I'm calculating mass of silver. Now, this is what I need to know. When I look at the current times the amps, I should get the charge per unit of time. So, I think that you might remember I believe in physics, they do Q equals IT, where this is equal to, the charge is equal to amps times seconds. And the amps times seconds would equal the charge, or the coulombs. So when I look at a question like this, I know that 1.5 amps, that is I, is passed for 15 minutes. What I can find from that is the coulombs, or the charge that has been applied. So Q equals 1.50 amps times 15 minutes. 15 minutes, and 1 minute is 60 seconds. Doing this, my answer comes out in coulombs. I get 1.35 times 10 to the third. Now again, remember, I'm taking silver ion and making silver solid. Back to the question. It's such that it's deposited. What is the mass of silver? Well, how do you get from coulombs to grams? Well, if we look up here, you're going to see there's something about a Faraday. So how do we relate charge that is applied to the electrons that are being removed? Well, the Faraday constant tells us that for every mole of electrons, it requires 96,500 coulombs. So, now when I go back, I can say, well, if there are 1.35 times 10 to the third coulombs, look up here, it says it takes 96,500 coulombs for every 1 mole of electrons to be removed.
Nonsense.
And then when you look at the problem, doesn't it tell me that for every 1 mole of electrons, you get 1 mole of silver? And 1 mole of silver is 107.9 grams. So that by applying a current of 1.5 amps for 15 minutes, I only get 1.5 grams. And again, the key to this is knowing that amps times seconds is a coulomb, and then how to get from coulombs to moles of electrons. Using that same idea, what I did was I have another problem that looks at a battery in your car. If the battery delivers 1.5 amps and its electrode contains 427 grams of lead, how long can the current flow before the lead electrode is consumed? So now I'm solving for time. Well, in order to solve for time, I need to know Q. Well, how do I know Q? I'm going to look at the grams of lead. So in this case, we're starting with the 427 grams of lead. If there are 427 grams of lead, there are 207? Find my periodic table here. 207.2 grams of lead for 1 mole of lead. So this would tell me how many moles of lead would have to be used up. For every 1 mole of lead that I use up, it loses how many electrons? 2 moles of electrons. So, 1 mole of lead uses up 2 moles of electrons. And every 1 mole of electrons requires 96,500 coulombs. And then I would solve this. When I do, I get 427 divided by 207.2 times 2 times 96,500 And I get 3.98 times 10 to the 1, 2, 3, 4, 5 coulombs. That's Q. That is equal to I. They tell me the amps are 1.5. And I can solve for T. So that T is equal to 2.65 times 10 to the 1, 2, 3, 4, 5th seconds. So I have the answer in seconds. If you wanted it in something else, I mean, that's approximately 73.6 hours. If they wanted it in hours or seconds, I mean, whichever answer they wanted, we could solve for. I think that satisfies the question. So there are really just a few of these. I mean, it seems like electrochem can be overwhelming. It's actually not too bad. Have some of those questions you can look at. I gave you the packet of notes, and that's really it. The best way to study is to look at the old questions. Okay?
Okay.
That's it.